Physical constants, the numerical values that dictate the mass and behavior of fundamental particles, often appear as continuous, fluid measurements. But beneath that fluidity, discrete algebraic geometries map onto these physical phenomena, anchoring them to sharp geometric peaks. The ODTBT constants program maps these values systematically. By evaluating specific mathematical averages, known as Grant means, from Pythagorean triples, the program successfully predicts the level 1 mass ratios for particles like the electron, muon, and proton, with error margins often below 1%. This chart maps the zero deviation vertex, or ZDV field. The green curve represents the proximity landscape. These predictions work because the specific particle seeds, like the proton seed marked here, rest at high proximity values, closely hugging the vertices of this field. We have to ask why this clustering occurs. We need to know whether the alignment of these specific seeds near the ZDV vertices is a random numerical accident, or if it is driven by a deeper underlying arithmetic structure. The extreme precision of these physical seeds within a strict mathematical landscape requires a structural explanation. For years, one highly attractive theory seemed to provide the answer. That theory is the Di-Domenico phi-commensurability hypothesis. It posits that the Grant means cluster at these vertices because their numerical values sit incredibly close to integer powers of the golden ratio, or phi. If this hypothesis were correct, the math should show a strong negative correlation. Means that are more highly commensurable with phi should reliably achieve higher proximity in the ZDV landscape. This scatter plot tests that assumption across all 9 Grant means for Pythagorean triples with a hypotenuse up to 300. Out of 423 distinct data points, the result is a total falsification. They scatter randomly, yielding a Pearson correlation of positive 0.047. A correlation of 0.047 is absolute statistical noise. It proves there is zero relationship between a value's proximity to the golden ratio and its position in the ZDV field. We must formally reject the Di-Domenico hypothesis. The golden ratio does not dictate the placement of these mass seeds. Without a single, unified scalar rule governing the entire landscape, we have to evaluate the numbers directly. The data reveals 4 completely distinct Diophantine mechanisms operating independently to create these high-proximity events. Discarding the phi theory forces us to examine the actual heterogeneous mathematical reality. The physical mass ratios of our universe are governed by a complex set of arithmetic rules. The first of these rules, mechanism A, dictates proximity through an irregular but strictly periodic family-level structure. We observe this by isolating the almost isosceles Pythagorean family, where the 2 legs differ by exactly 1, and tracking their root mean, or RM, values. As we progress through the family index to larger triangles, the RM mean grows monotonically. However, its phase residue behaves entirely differently. This graph tracks the RM phase residue proximity. Instead of a smooth progression, it oscillates irregularly, creating sporadic, sharp spikes. These resonance peaks hit at precise locations, specifically at family indices 5 and 7. The irregular gaps between these peaks are not random. They are strictly controlled by the continued fraction expansion of 2 pi over 3. The mathematical convergence of that continued fraction act as a structural clock. They perfectly dictate the exact sequence of when the RM residue will snap back to a ZDV vertex. Mechanism A suggests that some physical constants are anchored by deep, repeating geometric resonances embedded inside specific mathematical families. Mechanism B operates in stark contrast to the sweeping family laws of mechanism A. The eta meson seed relies on a highly localized mathematical anomaly. The eta meson utilizes the DHM mean of a single specific triangle, the 8, 15, 17 Pythagorean triple. This calculation yields an incredibly high ZDV proximity of 0.9969, placing it near a perfect vertex. The root cause of this proximity is a sheer arithmetic coincidence. The square of the triangle's hypotenuse, 17, is 289. This value happens to be almost exactly equal to 92 times pi, which is 289.027. This alignment controls the proximity via the leg structure, and it is entirely isolated.
The means of adjacent triples do not share this property. It is a localized accident on the number line. Mechanism D governs the muon and tau lepton seeds through a similarly isolated coincidence. Their means from the 5, 12, 13 triple fall on opposite immediate sides of the 8 pi over 3 ZDV vertex. The arithmetic mean evaluates to 17 over 2, or 8.5. The proximity of 8.5 to the 8.378 radian vertex is the reason these seeds achieve such high physical alignment. The data suggests that physical mass ratios occasionally map directly to isolated numerical coincidences in the number line, rather than broad structural laws. Mechanism C shifts away from specific triples entirely and introduces a broad recursive operation, scaling the depth of the H-alt mean. When we take the base H-alt mean of a primitive triple and multiply it by an integer scaling depth k, the resulting sequence of ZDV proximities forms a rigid dynamical system. This chart plots the ZDV proximity of the H-alt mean across 24 scaling depths, revealing 3 behavioral types. Type 1 climbs upward to lock where z approaches 1. Type 2 crashes downward toward 0. Type 3 refuses to converge, endlessly oscillating. This dynamic scaling behavior extends across the entire Pythagorean family. It is a separate structural root from the almost isosceles wave, or the isolated coincidences we examined earlier. For the type 1 triples, the math predicts a measurable transition plateau at scaling depths between 9 and 12, marking the threshold before terminal convergence takes over. Currently, predicting exactly which triple will fall into which of the 3 dynamical types remains an open analytical question in the program. Scaling operations expose hidden gravitational poles within the geometry. Through recursive iteration, the math forces specific particle seeds into precise, high-proximity alignment. We have falsified the phi-commensurability hypothesis and identified the 4 actual mechanisms controlling ZDV proximity. But we have to address a lingering contradiction. Phi still explicitly appears as a variable inside the system's lambda n lock potential equation. The golden ratio is utilized not for its clustering properties, but because it belongs to a specific category of algebraic integers known as Pisot-Vijayaraghavan, or PV numbers. A PV number is a real algebraic integer greater than 1, whose conjugate has a modulus strictly less than 1. Because the conjugate of phi is roughly 0.618, raising phi to successive powers causes the fractional part of the number to shrink, converging toward whole integers with absolute precision. This graph confirms that exactitude. It shows the ratio of phi's fractional part against its predicted exponential bound. For all values of n greater than or equal to 2, the ratio locks dead on 1.000 to machine precision. This exact PV property acts as a mathematical dampener. It provides the smooth, perfectly bounded exponential suppression envelope that the lock potential requires to function. If we substituted a non-PV base into the equation, the suppression curve would immediately break down, introducing chaotic, irregular fluctuations into the potential. The golden ratio does not actively group the particles. It exists in the formula passively, serving as a smooth, stable mathematical envelope for the actual Diophantine mechanisms to operate within. While phi dictates the suppression envelope, the actual frequency of the physical seeds is determined by the spacing between the maxima of the lock potential. It is critical to dispel the final misconception regarding the golden ratio here. The distance between these maxima is definitively not a function of phi powers. These 4 profiles map the lock potential for published particle seeds. The spacing between the peaks is driven purely by the specific phase strain, delta phi. The distance between successive maxima is analytically derived as 10 pi divided by delta phi, entirely independent of the golden ratio. The original phi-commensurability theory offered an elegant, unified explanation, but the data proves that the physical parameters of these particles rely on a heterogeneous mix of isolated numerical coincidences, recursive dynamic scaling, and strict structural waves. Ultimately, the discrete mathematical foundation of the physical universe consists of a complex taxonomy of distinct Diophantine behaviors.